only one good way to get good at drawing Lewis structures, and that's to practice drawing a lot of Lewis structures. So let's go through a few more examples, and we'll see some additional exceptions to the general rules of trying to fill the octets on all the atoms. So let's look at boron trifluoride, BF3. Let's look at POCl3, which is referred to as phosphoryl chloride. Let's look at N2O, which is nitrous oxide. And let's look at NO, which is nitric oxide. Nitric oxide is an important neurotransmitter. Nitrous oxide is laughing gas. If you've had your wisdom teeth out or something, they usually put you under with a little nitrous oxide, and then maybe not general anesthesia. And then let's also look at an oxyacid. Let's look at H2SO4. Recognized as sulfuric acid, one of the 6 or 7 common strong acids that we learned in general chemistry, along with perchloric acid, chloric acid, hydrochloric, hydrobromic, and hydroiodic acid, and nitric acid. So, what's the first thing that we always do? The starting point for all Lewis structures, which is always to count the valence electrons. So, 3 for the boron and 7 for each of the 3 fluorines, 24 electrons. That's a multiple of 8. So we can pretty much say that there are not going to be any lone pairs on the central atom. For phosphoryl chloride, phosphorus brought 5, oxygen brought 6, each of the fluorines brought 7. So that's 21 plus 6 is 26, plus 6 more is 32. Again, that's a multiple of 8, which means that there won't be any lone pairs on the central atom. Nitrous oxide, nitrogen brought 5, oxygen brought 6, 16 electrons. Again, it's a multiple of 8, so the central atom won't have any lone pairs. Nitric oxide is a little odd. Nitric oxide actually has an odd number of electrons, 5 for the nitrogen, 6 for the oxygen, so 11 total. And that means that we're not going to be able to have all paired up electrons. For sulfuric acid, each hydrogen brought 1, sulfur brought 6, each of the oxygens also brought 6. It's going to have 32 electrons. Immediately another multiple of 8. So none of these molecules are going to have lone pairs on their central atom the way phosphorus trichloride did. Phosphoryl chloride or phosphorus oxychloride actually looks a lot like phosphorus trichloride, except that instead of having a lone pair on phosphorus, it has an additional outer atom, in this case an oxygen. So step 1 was to count the valence electrons. We have to get that right. If they're the wrong number of electrons in your Lewis structure, everything else about your Lewis structure is wrong. Next step, pick the central atom, the least electronegative atom. In this case, boron is the central atom. Phosphorus is less electronegative than oxygen and less electronegative than chlorine. It's to the left of chlorine and it's below oxygen as well as to the left. Phosphorus is the least electronegative atom. It's written first, although that's no guarantee. Nitrogen is less electronegative than oxygen. So the central atom, even though there's only one oxygen, right, N2O looks a lot like H2O at first glance, and oxygen is the central atom in H2O, but nitrogen is less electronegative. So for nitrous oxide, nitrogen is the central atom. There is no central atom for nitric oxide. You can skip immediately to the step of putting a single bond between the 2 atoms. And in sulfuric acid, the least electronegative element is hydrogen, but hydrogen can't be in the center. So So the central atom must be sulfur. We can now move on to the third step, which is to form a single bond to each of the outer atoms. Single bond to each fluorine. Phosphorus, a single bond to the oxygen, and also a single bond to each chlorine. Single bond to the oxygen, single bond to the other nitrogen. Nitric oxide is already done, and sulfuric acid, single bond to each of the four oxygens. And then we have to remember that when we have an oxyacid, sulfuric acid, nitric acid, perchloric acid, hypochlorous acid, nitrous acid, phosphoric acid, any of the oxyacids, the hydrogens are not bound to the central atom. The hydrogens are bound to oxygens. It doesn't matter which two oxygens we choose to attach the hydrogen to, but we need to attach those two hydrogens to oxygen, not to sulfur. You're going to get this wrong on a quiz. I'm telling you, don't do it. Right? Oxyacids have oxygen attached to hydrogen, hydrogen attached to the outer oxygen. So now we have the framework built. Step 4 would be if there are additional electrons, which there are in all these cases, we need to fill the octets on the outer atoms. Right? We use 6. There are 18 electrons remaining. And we're going to put those 18 electrons around the fluorine. That actually uses up all of the 24 electrons, 8, right? 8 around each fluorine, that's 24. 32 electrons, we've used 8. We've got 24 remaining. And we're going to fill the octet on all 4 of the outer atoms, and that's going to use up the remaining 18 electrons. 32 electrons total, 8 around each outer atom. Good. Nitrous oxide, we use 4. 12 electrons remaining. First 6 on more electronegative oxygen, and the remaining 6 on the less electronegative nitrogen. We have 9 left. Put the first 6 on the more electronegative oxygen, the remaining 3 on the nitrogen. And in the case of sulfuric acid, we use 12, forming 6 bonds. We've got 20 electrons remaining. We're going to fill the octet on the 2 oxygens that are not bound to hydrogen. That uses up 12 of them. You got 8 more, 4 on this oxygen, 4 on that oxygen. Used up all of our electrons. There are no electrons left in any of these cases. So in all of these cases, we have structures that have no lone pairs on the central atom. But we're not finished. We're not finished. We don't have a filled octet on boron. Kind of like to have a filled octet on boron. One way to have a filled octet on boron would be to form a double bond between boron and one of the fluorines. And because the 3 fluorines are identical, there are 3 equivalent ways that we could actually do that. Phosphorus has a filled octet, it's happy. Nitrogen does not have a filled octet. We're going to need to form multiple bonds. We could form a double bond on each side by taking 1 pair of electrons from the oxygen and 1 pair of electrons from the other nitrogen. Form a structure that looks like that. That would be exactly like the structure for CO2. We could also form a structure by taking 2 lone pairs from nitrogen and forming a triple bond on one side and leaving a single bond on the other side. And in theory, we could do it the other way around as well. Take both lone pairs from oxygen. And those would all be resonance structures. how do you know when something is a resonance structure? It's a resonance structure if all you move is electrons and you do not move any, and all we do is interchange lone pairs and pi bonds, then we have a resonance structure. We're not going to be able to keep everybody happy here. There's nothing we can do. We can form a single bond by taking one of those pairs of electrons from the oxygen, but that's still going to leave nitrogen with an unfilled octet because there's a single electron. We have to put the single electron somewhere. We can either put the single electron on nitrogen, or in theory, we can put the single electron on oxygen. Those are resonance structures. This is happening. Right? Sulfur already has a filled octet. It's all good. Next thing we have to do is assign formal charge. In this case, each of these two fluorines is happy because each one has 7 electrons, 6 lone pair electrons, and half the bonding pair electrons. Its valence with 7 is good. This fluorine, on the other hand, is not happy. It's only taking with it 6 electrons. It brought 7, right? If we really like to take with it 7, it only takes 6. It's electron deficient. It actually has a formal positive charge. The boron only brought 3, but it has a -1 formal charge. That's not great, because boron is significantly less electron dense. It's the best Lewis structure you can do that doesn't break the octet rule. But generally, when we draw the Lewis structure for boron trifluoride, we're going to leave it like that. That reflects how the molecule reacts. Boron is electron deficient. So when you have a central atom that had a valence of less than 4, it's okay to leave the central atom with an unfilled octet. Right? But only when you have an element that had a valence of less than 4 to begin with. Boron, beryllium, aluminum, things like that. The better Lewis structure for the octet rule is this one that has a double bond to fluorine. That's how you. Chlorines are happy. They brought 7 electrons. They're taking 7 electrons with them. Phosphorus isn't happy. Phosphorus brought 5 electrons. It now only has 4 to its name, so it's electron deficient. It has a positive formal charge. Oxygen, as we said, right? Anytime you have 3 lone pairs and 1 bond to oxygen, oxygen is always going to have a -1 formal charge. Because that's not the best structure for phosphoryl chloride. Turns out that when you have an element in the 3rd row or below, it's better to minimize the formal charge by expanding the octet. Expanding octet is only allowed if you're in the 3rd row or lower. So you can't do it with nitrogen, you can't do it with fluorine, you can't do it with carbon. You can't do it with phosphorus. The better Lewis structure for phosphoryl chloride is the one with the pi bond to oxygen, because that now leaves the phosphorus with no formal charge. It has 5 electrons, that's how many electrons, that's how many it brought. So the better structure is the expanded octet. Phosphorus, those are the most common row 3 elements that are going to expand the octet. And we can actually jump all the way over here. The sulfuric acid, the way we've drawn each of those oxygens has a formal -1 charge. Sulfur now only takes 4 electrons with it, but it came with 6. It has really unfavorable for the octet on sulfur by forming double bonds to each of the oxygens that have no hydrogen attached. And then having the formal charge be 0 on all of the elements. So when you see sulfuric acid, you'll see it drawn like that, with 2 double bonded oxygens, 2 single bonded oxygens, and no formal charge. In general, you'd like to minimize formal charge when possible. And if you have a 3rd row element or below, you can minimize that formal charge by forming pi bonds and expanding the octet of your central atom. What about nitrous oxide? How are we going to determine which of those resonance structures is the better of the bunch? What about nitric oxide? how are we going to determine which of those two resonance structures is the better of the two? The way we're going to do that is we're going to assign formal charge, and then we're going to look for as little formal charge as possible, and formal charge such that the minus charge is on the more electronegative element. This one is obviously garbage. That structure is no good because that structure doesn't have a filled octet on all the atoms. So in this top structure, nitrogen has 4 bonds. Anytime nitrogen has 4 bonds, it always has a plus formal charge on it. Nitrogen has 4 bonds on every one of these 3 resonance structures. So that central nitrogen in all cases has a formal positive charge. Which means somebody has to have a negative charge on it, because it has to add up to neutrality. Nitric oxide, nitrous oxide is the neutral molecule. This oxygen is happy, right? 4 lone pair electrons, 2 bonding pair electrons, that's the 6 that it came with. This nitrogen has 4 lone pair electrons plus 2 bonding electrons. It actually has 6, but it only brought 5. So that nitrogen has a negative formal charge. In this case, the nitrogen is happy, has these 2 electrons at half of these 6, so 3. That's 5, that's what it brought. Oxygen has 6 lone pair electrons at half of its bond. That's 7, it only brought 6. Has a minus formal charge on it. Anytime oxygen has a single bond with 3 lone pairs, minus formal charge. To have a neutral, no formal charge, oxygen wants to have 2 lone pairs and 2 bonds. In this case, oxygen has 1 lone pair and 3 bonds, which means only 5 electrons that it gets to take with it. It actually also has a plus formal charge on it. 3 bonds to oxygen and 1 lone pair, always a plus formal charge. This nitrogen has a 2 minus charge on it because it takes those 6 electrons, which is already 1 more than it brought, and half of the bonding electrons, which is 2 more than it brought. Right? Negative 2 formal charge. This is by far the worst of these 3 because it has formal charge on all 3 atoms and a negative 2, right? You usually don't want formal charges that are greater than 1. Between these 2, we're going to choose the middle one, the triple bond to the nitrogen and the single bond to the oxygen, by virtue of the fact that the negative charge here, the negative formal charge, is on the more electronegative oxygen rather than the less electronegative nitrogen. So it's not symmetrical, right? Triple bond to the nitrogen, single bond to the oxygen, but it's better than the symmetrical structure because the negative charge is on the more electronegative element. What about nitric oxide? Well, if we're looking at nitric oxide, we're saying formal charge. In this case, nitrogen has 4 electrons to its name. Has 4, brought 5, that's no good. Plus formal charge. Oxygen has minus formal charge. It's got the negative charge on the right atom, but it's really got a very electron efficient nitrogen. Only 5 electrons, not 8. That's a long way from the octet. In this case, nitrogen takes 5 electrons with it. It brought 5. That's happy. Oxygen has 6, brought 6. No formal charge on that one. In this case, nitrogen now takes 6 with it, but it only brought 5, which means it has a negative formal charge. Oxygen takes with it 5. It only brought 6. Positive charge. That's not great. The best you can do is that middle structure that has 1 missing electron on nitrogen. When you have an odd number of electrons, you can't fill the octets on everybody. You can't pair up all your electrons. There's no way to accomplish that. You can't do a triple bond to solve the octet problem on nitrogen, because that would mean expanding the octet on nitrogen. Nitrogen isn't able to expand the octet. So we can't do what we did with carbon monoxide. With carbon monoxide, our best structure looked like this. It had a triple bond between the atoms. Nitric oxide has 1 more electron than carbon monoxide, which means you have to expand the octet if you form a triple bond. You're not allowed to expand the octet on a second row element. So we can't fix the problem.